Okay, so for your midterm exam, you are going to have 2 problems from Module 2 and 2 problems from Module 3. Module 2. Okay, Module 2 was resultants of concurrent force systems. So resultants of concurrent force systems. Okay, what concurrent force systems mean is that your forces share a common point. And they share the common point either by point of application, or if we extend them along their line of action, they are going to have a common intersection point. So what we saw a lot of times was an XY axis, and we saw, for instance, force here, a force here, maybe a force going down. So you might have had an F1, an F2, an F3. Then we knew what the angles were. I'm going to say 30 degrees, 60 degrees, and then vertical. And we want to find the one force, the resultant, that would replace those 3, but have the same net effect on that point of application. Okay. So then what you do is by rectangular component method, and that's what I'm going to require you guys to do. You're not going to have a choice on the exam. Okay. You're first going to draw your diagram and add your convention, right? Number 2, you're going to break any forces into components, okay? Number 3, you're going to sum your forces in your, I should say X and Y. X equal to your RX component. You're going to write this out, and then you're immediately below, you're going to do that work. Then you're going to sum your forces in the Y to get the resultant Y component. I'm going to see that above where you do it. Don't sneak this in. So don't go through the problem, figure it out, and be like, oh yeah, she wanted me to put this in, and I'm just going to write it alongside. I take off points for that. Remember, you are writing this in a way so that I can follow it along, so that if you would be handing this to somebody where you're working, that they would be able to follow your work and understand what you did. Okay. So you're going to, these tell me what you're going to do before you do it. Right. Then your step number 4 is you're going to find your resultant. It's going to be equal to the square root of the RX squared plus the RY squared. Okay. You're also going to find theta. That's going to locate it with respect to horizontal or vertical axis. And then you are going to draw me a diagram, okay, of your results. That lets me know that when you calculated the resultant of the angle, you know where it's at, okay? Up here, don't forget, you have to also show, as long as we're talking diagrams, you have to show your components. Components are always going to be on the X and Y axis, not floating. We don't do floaters, okay? Same thing here. So we've got another one, F2Y, F2X. So everything is going to be labeled so that when you do your components, if I see an F2X that you calculated, I'm going to look up here and I'm going to see it in your diagram. And it's going to be placed appropriately. So 2 problems, Module 2, resultants of concurrent force systems using the rectangular component method. So as I said, Module 1 was doing math. We did some right angle trig. We found components. We did units. All of those things are actually kind of in here already. So that's why I'm not giving you specific problems for Module 1. All right, so I'm going to peek back at what we had for homework. Are there any questions on any of these application problems from Module 2? Okay. All right. Then let's look at Module 3. Module 3 application problems. These expire tonight. Okay, so if you haven't finished up Module 3 yet, this is actually Chapter 2 in our McGraw-Hill book. This is looking at equilibrium. Oh, Connor, You want to go back? Okay. Shoots, I wish you would have said something a little bit earlier. 31. Wait a second. 31. Let me look here. We've looked at that one a couple times in our sessions. Hold on. I'm wondering if I have a video of that one. Not that I want to avoid it. Dot, 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 dot. Oh, I guess not. I know I've talked about it. I mustn't have taken a video of it. Problem 2.6. Okay. All right. So when you say, do you want to go over the whole thing? Or is there a specific part that you're interested in? Just want to. Locate it here. So Connor, when you say look at it, do you mean you want to work the whole thing, or do you just want to relook at how to solve it? The equations is what I'm confused about. Oh, okay. Yeah. Okay. So let's look at number 31. Now, this one is worked out already, so I'm going to kind of go through the process because it sounds like you are just focusing on the equations to solve. Let me get this out of the background. Okay, so 31, where we're starting, is going to be our diagram, okay? I'm going to put my convention up here so we are legit, okay? Now, what we have going on is we have a 500 Newton force, okay? We have a 200 Newton force. And then we have this cable that's going down that's holding up, I think it's like a pole of some sort, right? And what we need to find is what is the force along this cable, if I remember correctly. Now I better look at the problem. I just gotta find the problem. Sorry. In the book, they're scattered throughout. So. Okay. Here's the problem. So we want to find what is the force along this cable when we have the other two forces acting. Now, in the case of the other two forces, they gave us the slope of those lines. So you need to calculate the angles for each, okay? And then this is what we're going to be going along. And that's going to be along the lines that we see here from the distances over from the pole and up. So I just want to be sure, Connor, like where you're starting, were you able to get the angles of each one of those as well as the pole and then calculate the components that we see here? Yes. Okay, great. So it sounds like you're ready to go and look at the equations, right? That's what you were focusing on. So the first equation that you're going to look at, and it really doesn't matter which one, but because we know a little bit more in the y direction, we are going to sum our forces in the y direction. That is going to give us our resultant y. Now, for this problem, it told us that the resultant is going to be horizontal only, right? And so there isn't going to be a y component in the y direction of the resultant. So that means even though, yeah, we can say this is going to be the resultant y component, but it's also equal to 0 because everything about this resultant is going to be horizontal. So I'm going to jump to the end here. Our entire resultant is going to be just in that horizontal direction or along the x-axis. So that's why we're going to set this equal to 0, not because it's in equilibrium, but because the problem said that the resultant is horizontal, okay? But we still need to solve from some unknowns here. So we know what AY is, we know what BY is, and DY is the unknown then. So we set that equal to 0, and then we can solve for DY equal to 20 newtons, okay? So now that we know that dy is 20 newtons, if we have the 48.9 degrees as the angle over here for the direction of that cable, then we can calculate what the dx is going to be, okay? So on the other side here, we find the x component of dx, and we know that to be 17.447. And now we are going to sum our forces in the x direction, which we can say is the resultant x component, but that now, because the resultant has to be only in the x direction, that's also going to be the actual resultant because there is no y component. So now we can say negative dx, it's pointing to the left, plus ax plus bx is equal to our resultant. So then putting those numbers in place, now we get our resultant equal to 640, all going to the right. And then here's the diagram down below. Is that helpful, Connor, what you needed? Okay, good. Good. Yeah, that one's worded a little bit differently just because of that resultant being horizontal. It changes that y equation a little bit, right? Okay. Any others from module 2? Peek back here one more time. All right. Any others from here? Okay. If not, then I'm gonna go down to module 3 application problems. Okay. So here we have 5 application problems. In this case, this was looking at equilibrium of concurrent force systems. Okay, equilibrium of concurrent force systems. So find paper here. Now, concurrent force systems means the same thing to us. It means that we are working with forces that have a common point, okay? So module 3, this is equilibrium of concurrent force systems, okay? This is also going to have our convention. Yes, we aren't using moments just yet, but if you want to just, I think someone asked last time, can I add that in there? Absolutely. It's not going to hurt anything, whether you use it or not. It just completes our convention. So in this case, when we have concurrent force systems, we're going to have our x and y axis again. And we're going to have, for instance, a series of forces that are in equilibrium. I'll kind of use the same scheme that we had before, okay? We can say maybe the one going down is 100 pounds. The one going this way is 250 pounds, and it is at a 15-degree angle. And then we're going to call this one, let's say F3, and it's at a, I don't know, 75-degree angle. And what we want to find is find the magnitude of F3 to keep this all in equilibrium. So if this force system is balanced and in equilibrium, now we just want to figure out what is the magnitude of that one force, okay? So you're going to use the rectangular component method. So I'll say that, rectangular component method. And I dictate that all your problems that you're going to do, all 4 are rectangular component method. So part number 1 is going to be, first thing is going to be any components that you have to figure out. Okay, so anything that's not on the x and y axis, we want to get it there. Then number 2, you're going to use your equations of equilibrium. Okay, there's 2 equations of equilibrium in module 3. The sum of the forces in the why do I always do y first? I don't know why I'm thinking that. X first, x, and sum of the forces in the y, both equaling 0. This is one of those things too. When you're using these equations of equilibrium, you have to write this before you actually do it. Don't just jump into writing numbers and then at the end, oh yeah, I was supposed to put that in there, okay? This is like telling me what you're going to do and then immediately down below do it, okay? So you're going to use those 2 equations of equilibrium. What ends up happening is that you end up with two equations with the same two unknowns, okay? And then you're going to use the substitution method to solve for those two variables. That's something that we did, I think, in almost every single one of the problems that we had in that chapter, okay, or in that module, all right? And then, yeah, that's it. That's it. You don't need to do a diagram here because you're going to have all of that stuff up here. If there's anything that you need to break into components, then you need to be drawing the components, labeling them, you know, with the appropriate call out, so that if I'm seeing an F3X and an F3Y in my components, I'm seeing it up here. Okay, same thing for any other forces. Making sure that you're putting your units in all phases of the problem. Make sure that you're canceling and or combining. Okay, that your final units that are coming out are appropriate for forces and such. Okay, so that's kind of the gist of Module 3. So this was equations of equilibrium of concurrent force systems. So finding when we have them, how are they going to balance? What do they have to be in order to balance? In order to, you know, equal to 0. So I'm going to go back to Module 3. These were the 5 problems that you were given that all kind of had that same sort of flavor, if you would. So are there any questions on any one of these homework problems here? I'm not seeing anything yet in the chat box. So I'll ask one more time. Any questions on anything in Module 3 application problems? Remember, this is preparing you for the midterm exam. So now is the time because we can work through these. Okay, no one's asking. So again, I'm not gonna do any problems if I don't want to waste anybody's time. Okay, so if there are no questions, all right, if there are no questions, then that's really all I have for our review. So I'm gonna stop the recording at this time.